welcome back. In this section, we're going to talk about energy sources that we have for muscle contraction. And the good news is you already should know most of this section. So let's start with reviewing cellular respiration, our basic equation. Hopefully you know this. If not, let's make sure you do. So the reactions are starting with sugar and oxygen. Think about what those trees make. They make sap that we make maple sugar from and oxygen. Yeah, and from those, we're going to have waste product of carbon dioxide, a waste product of water, and what we really want, energy. So how do we do this? Well, we do it in a 4-step process. The first step was glycolysis. This happens in the cytosol. At the end of that, we have taken the 6-carbon sugar, for instance, glucose, and ended up with 2 3-carbon sugars. We have created some ATP, but we've also created some electron carriers in NADH. If oxygen is present, then the product of glycolysis, the pyruvic acid, moves into the mitochondria. And in the matrix, we will have our linking reaction. At the end of the linking reaction, the acetyl-CoA will then enter the Krebs cycle. We will also have produced some carbon dioxide and more NADH. In the Krebs cycle, we will create more carbon dioxide. In the mitochondrial matrix, we will also create more electron carriers in both NADH and FADH2. And remember, because we have 2 3-carbon sugars, we do the Krebs cycle twice for every 1 molecule of glucose. At the end of this, all the electron carriers go to the mitochondrial cristae, where they do the electron transport chain, and they use the oxygen that was produced by the plants. And we have a waste product of water. But the net result at the end of cellular respiration is, in a perfect world, we would end up with 36 ATPs. Now, what happens if we don't have oxygen? Well, then nothing moves into the mitochondria, and we have anaerobic respiration. And so there's 2 different things that could happen. The first is that pyruvate could end up forming ethanol or alcohol. And so you would only end up with the energy formed through glycolysis. The second option is that pyruvate could end up forming lactic acid. So with anaerobic respiration, you either make alcohol or lactic acid. Lactic acid's what our bodies typically make. And we only have a net of 2 ATP produced from glycolysis instead of the massive amount, 36, hopefully, ATP produced from cellular respiration. Realizing, of course, if we're not starting with a glucose molecule, if we're starting with lipids or proteins, we will be entering later. And so we will be making maybe only 32 or 28 ATPs, but we certainly will be making a lot more than just 2 ATPs. All right. So if you've gone to the gym, or you know people who've gone to the gym and they talk to trainers, you may know that they take substance called creatine because they've been told, oh, you want to work out, you want to work your muscles, you need to make creatine phosphate. Okay. So here's the thing about creatine phosphate, sometimes called phosphocreatine. Okay. Our bodies make ATP 24/7, 365. Even when you're sleeping, it is constantly made, but our body can't store all that ATP. Okay. So what the body does, that extra ATP is used to make creatine phosphate, also known as phosphocreatine. So here we are, ADP is being used to make ATP. And then there's an enzyme which will take one of those phosphates from ATP, that high energy bond, and will use it to attach it to creatine to make phosphocreatine or creatine phosphate. And that can be stored in your body. And then when more ATP is needed, the same enzyme that made the creatine phosphate can be used to break it down, and the phosphate will come off the creatine, be attached to ADP to make ATP, and so now you have more energy for muscle contraction than just the 10 seconds worth of ATP that was stored in the muscle. So, at rest, ATP is used to make phosphocreatine. At exercise, phosphocreatine is used to make ATP. So this is a reversible equation, goes back and forth. So what does this mean? When it comes to energy source, if we were to load you with a lot of creatine phosphate, the powder, and if you were to take it for a week, it's going to improve your power, but it only lasts for a few seconds. I'll be showing you shortly. But the problem with creatine phosphate, it creates a huge osmotic pull into the myocytes. So do you remember what osmosis was? It was diffusion of water. Okay. So if we have creatine phosphate being stored in our muscle, what that means is that muscle is going to suck in a massive amount of water into that muscle. Those muscle cells are going to fill up with water. That water is going to come out of your bloodstream. So you are going to be dehydrated. You're going to have diarrhea. You're going to have muscle cramps. You're going to have kidney damage. This is going to be 10 times worse if you're taking any kind of caffeinated beverages or alcohol. So if you know people who go to the gym, and we've all seen people at the gym sitting there drinking their Starbucks. Or if you know people who go to the gym and they do their creatine powder and then you see them on the weekend having their beer, drinking their shots, going out in the evening, they're at huge risk for kidney and muscle damage. So don't do this, okay? Unless you are a professional athlete, do not do this. And the professional athletes aren't going to doing this aren't going to be the ones who are running races. They're going to be the ones who are like doing clean and jerk where they need like to hold something for 3 seconds. And here is why. If we look at all of our energy sources, let's start with the yellow. Yellow is the ATP stored in your body. If we look at just the ATP stored in the body and imagine you're on the treadmill or you're on the elliptical and you start running or pushing the bicycle, what you will notice is, sorry about that, within the first 3 steps, you have used up all your ATP stores. 2 seconds and your ATP storage is gone. But remember, even without taking creatine phosphate, your body has stored ATP as creatine phosphate, okay? So you do have storage. And so that is our creatine phosphate storage in purple. And so as your ATP stores are going down, your creatine phosphate is being used. You're starting to break it down to ATP, and that's peaking right about the time you're running out of ATP is your peak creatine phosphate usage. And then you are running out of that. And if you have stored from using this, you are now out of it at 10 seconds. So you're spending a lot of money buying a lot of power to get you 10 seconds worth of energy. Yeah, that's it. Okay. Now, the rest of us, we ran out of power before 10 seconds from that. So, what are the rest of us doing? We're doing anaerobic, lack of oxygen. So, have you ever started working out and when you're about a minute or two in, you go, holy crap, this is a lot harder than I remembered it being last week. Like, is this the right setting? Did I make it harder? It's like, I remember last week doing this and it didn't seem so hard. Yeah. The first minute or two are really hard because you're generating lactic acid, because your aerobic system takes a few minutes to catch up, especially if you didn't warm up to increase your blood flow before you started working out. Okay. Once your aerobic system kicks in, then yes, you're able to do that steady state for a couple of hours. Okay, that's it for this section. Hopefully, you didn't find it too bad. So, if you didn't quite get that cellular respiration, if you're one of those people on the first test thought cellular respiration has something to do with breathing and moving oxygen in and out of your lungs, go back and learn about cellular respiration for this second test. Okay, you're going to need to know this. Okay, thank you so much, and I'll see you when we come back. And now we're going to start talking about twitchy muscle fibers when we come back, which is really cool. You'll figure out what kind of athlete you really should have been when you were competing in high school. See you soon.